Hello, everyone. Happy April Fools. I hope you liked the big announcement. Today we're going to be talking about a math topic called partial fraction expansion. So we're going to switch the screen over. I have a new background to show you guys. I'm pretty proud of this one. I hope the mic isn't maxing out like it was the other day. I don't know. It's kind of hard to test it because I always boost the mic on the stream. So we'll see how it sounds. But I'm going to switch the screen over and we're going to get right into it. So as of right now, I have the paint screen up here, and let me switch my screens around so I can make sure that I'm visible, and then I'll also make sure I can see the chat just in case there's anyone asking questions. So as you can see on the screen, we have a paint window up. We're going to be talking about partial fraction expansion. So I'm going to write that over on the top here. Partial fraction expansion. Okay, so this is a pretty common math topic. Once you get into some of the engineering divisions and even just in some of the prerequisite math courses that are needed for engineering tracks. I'm sure that these prerequisites will also be necessary for other divisions. Sorry about that. I don't know what's going on with the car outside. What exactly am I talking about? Well, you'll see there's an example up here, and we're going to get to that in a second. But to start off, I'm just going to sort of explain what partial fraction expansion is. So basically what we have is we're going to have something in this shape. So we're going to have a numerator of some function and a denominator of some function. Now, in most cases, this numerator is going to be a lesser power than the denominator, meaning that there is a lower power as the highest power of the variable in this polynomial that we're seeing on the top than on the bottom. So if we just pick a arbitrary version of this, we'll kind of model it after this, so we could have some a times s, just a times s plus b over some s cubed plus cs squared plus ds. So the reason that we are looking at this is because there are a lot of zeros and solutions on the bottom, and we want to spread this out because let's say we wanted to differentiate the whole thing or integrate the whole thing. Well, it's a little bit more difficult to do that with it in this fraction form. So what we're going to do is we're going to attempt to make this into several individual fractions, because then we won't have as much on the top and the bottom. So there are other things that this is useful for, like Laplace transform, which you might see from me using S here. That's actually the most recent time that I've used it. But there's a lot of different reasons that we would want to split a large polynomial fraction up into smaller fractions. So what the idea of partial fraction expansion is we want to have this set equal to some other function here. So if we factorize this, then we can pull an s out, and then we will also be able to factor each of these. So let's just go general here. Let's say that there's some constant here over one of our factors plus another constant over another factor, and I'm going to call that p, and then some final constant over our third factor, because we have a third power here. So that means there's going to be 3 zeros that can come out of this. So this is going to be P1 minus P2. So this is just an arbitrary selection. There are more general cases for explaining this, but I just wanted to show you guys an example. So there's a couple different tactics, because what we need to do is we need to find these constants. We're assuming that we know all these coefficients, as like in our example up here, but what we're trying to find is what goes on top of this of these fractions here. And so there is a proof for how to show that this actually works. I'm not going to go through that at this moment because I feel like it would take up too much time, and I want to just show you the application of solving for these coefficients. So there's a couple tricks we need to do, because if you know, anytime you want to solve for coefficients or solve for constants, we need to set up a systems of equations, because there's more than one unknown that we have here. Now, you can also say that our variable s is an unknown, but we're assuming that we have some data on this, or at least we are able to put inputs in, so s can really be whatever we want it to be. So that's an interesting idea, and you'll see what I mean by that when we get into the actual example. So there's a couple different things we can do here to get started. So what we need to do is we need to isolate these variables in order to create a list of equations. The easiest way is to make it so we cancel out other variables. So this is something that just makes our lives easier and will hopefully make the math easier as well. So so there's a couple different ways we can do this. The way that I like to usually do this is I like to multiply and get a common denominator. So what that means is we're going to make everything have this denominator. But since this is a multiplication of all of these factors, then each of these will have the other two factors. So I'm saying 2 because this is the example we're working with. Obviously, this could be expanded to more or less, but just keep that in mind. So if we expand this, so I'm gonna write down these, but I'm gonna explain them individually. So we try to find the LCD, which is the least common denominator, and we are going to make it so that each of the coefficients is not in a fraction. This will make our lives easier. So this is not a necessary step, but it does definitely make it easier. So what this means is we would multiply this out, and we would have AS plus B is equal to our S minus P1 times S minus P2 times A, and then the same for the others, but excluding the one that is currently in their denominator, because when we multiply this through, this guy would cancel with the one on the top. So we're going to have an S times S minus P1 times B, and I think you get the picture because I'm kind of running out of space here, but you can do the same for C. So like I said, this is kind of just a organizational idea. It keeps our system a little bit easier to read, and it makes it a little bit more simpler. So what we can see here is now there are ways we can make this cancel out some. So there's two different ways to approach after setting it up in this form. The first way is going to be we can plug in a number that will cancel out. Plug in one of the zeros actually. So if we have P1, P2, or in this case 0 for S, we can plug these in, and because there is only one that does not have that particular factor being multiplied to it, it will be the only one left over. So let's say we picked 0. Actually, no. Let's pick P1 just to make this a little bit more general. So we're gonna pick a 0. So if we picked a 0, let's pick P1. Then we would have A times I'm just not gonna put it in parentheses. A times P1 plus B is equal to, so here we have S minus P1. So when we plug P1 in here, we're going to have a 0, and it doesn't matter what happens here because it's already being multiplied by 0. So the A is gone. And here you can see that we also have S minus P1. So when we plug when we plug P1 into here, we're going to have a 0 as well, so it doesn't matter what happens with this S over here, and B will be canceled out. So the only term we're going to be having left is our C term multiplied by, so if we remember, it is the other two denominators. I'm sorry, this should actually be P2 right here. So the correction is that we are only going to have B here, because if you remember, we would cancel out this denominator, and we'd have S and S minus P1 left over for C. So C would cancel out. So what we're going to have is we're going to have P1 times times P1 minus P2 times B. So from here on, we can simply solve for B, and we should know all of these other numbers because we plugged P1 in. We'll know what P2 is because we factored this out, and we know what A and B are. So that's just something we mentioned in the start because it's from our that's what we're going to be having in our example. So you can solve for B, and you can do the same for every single variable. Now there is a case where we could have a different situation. So if something doesn't factor out in a real sense, so if we only have imaginary solutions to this factorization, then what we do is we leave this in a different form. So let's say that we had just a factor that was imaginary. Then we can what we can do is we can say that this is going to be AS plus B times our S squared plus I don't know, let's think of something that's going to be imaginary. So I'm trying to think if we have a 2s plus 1, so this would come down to s plus 1 squared, and when we take the square root of that, we would get positive and negative I. And so the reason that we don't change this is because a lot of people tend to have a problem with working through complex numbers. So instead of having one constant to solve for in the top for each individual what's it called, 0, we have two constants to solve for the couple of imaginaries. But when it gets to this step, we don't necessarily want to pick those imaginary numbers because that might complicate the math. So what we can do is a third option here is we can pick just a number. So some easy numbers. So I'm just going to say pick a number. And so some suggestions would possibly be 0. That's usually a nice one. 0 happens to be a solution in this one, so we will already have been using that. You can also pick 1. That just makes the math a little bit easier. And -1 will keep the math pretty simple as well. We don't want the numbers to get too big. Perhaps you're doing this on a test and you're trying to do this in your head as opposed to plugging stuff into the calculator just to save time. You want to pick numbers that are friendly for you. So as you get better at this and as you get some more experience, you'll be able to pick numbers here that will show off what you have a little bit easier. So this might not cancel anything out, but perhaps by this time we've already gained enough information about the other constants here that we can just use those constants and plug them into our equation that we get when we plug in 0, 1, -1, or any number really. So I might show you that during the example, but that's just what I'm going to be explaining in a little bit. And so our fourth option is actually something a little bit different from these guys right here. Our fourth option is you can actually take the coefficients of each variable and multiply them, and set them equal to each other. So this is pretty common. So what's happening is since we have an AS here, that means that A is equal to the addition of all of the constants that were, I'm just being arbitrary down here, I'm not necessarily following the example, but A is equal to all of the constants that are multiplying, all of the coefficients of a single powered S. So if there was a s squared term, so let's say z s squared here, then that would mean that z is equal to all of our terms that have an s squared in them added together. So that's something that we will look at with the example, but these are the four tactics. So the uh, the four possibilities of getting to an answer. The first one isn't necessarily how to get to an answer, it's just kind of making your life easier. And the rest of them are definitely ways that you can make the solution present itself. Um, so I'm going to copy this guy over here and we're going to get into the example. So I'm going to just cut this guy out and then we're going to get a new screen and we're going to paste him in. Alright, so this is our example. So I'm going to write EX over here. And so this is what we're working with. We're just going to say, I don't know, y of s is equal to this function here. And we want to find the partial fraction expansion of this function. So the first thing we need to do is we need to factor the bottom here. Now, I've done this problem already, so I should know this off the top of my head, but we'll see. And I have work on this over to the side just in case I need to check anything to make sure I'm not making any mistakes here. But obviously the first thing we can do is we can pull an s out front, and I believe what happens is we have another situation where we're going to have complex roots here. So I wanted to make this a sort of general example to also include that complex root idea. So I'm going to factor this out here, and we have plus 10. And so what we see is that we shouldn't necessarily mess with this one, because what's going to happen is we're going to have s plus something squared. And what that, sorry, I hit the mic. What that's going to do is it will create a complex conjugate pairing, and that would make life a little bit hard for us. So what we are going to do instead is we're going to leave this here, and we're going to put individual coefficients for one for s and one for s to the power 0. So let me rewrite this guy down here. So we're going to go 3s plus 6 over s times s squared plus 2s plus 10 is equal to, so we're going to put one constant, over s plus, we're going to have 2 here. So we're going to have a bs plus c over our second, our complex conjugate pairing. So that's s squared plus 2s plus 10. And so this is the situation we're going to work with. But like I said, it's a lot easier to multiply this out by the common denominator. So what we're going to do is we're going to say 3s plus 6 is equal to a times our s squared plus 2s plus 10. Sorry, I didn't finish out the parentheses up there. Plus our bs plus c times s. So, sorry, that's not the correct way to write that out. So let me put this in parentheses and then put the s outside the parentheses. There we go. Okay, so there are, like I said, about 3 options we can do after this in order to get to a solution. So we're going to start with the first one. We can see that 0 is definitely a solution. So we are going to plug 0 in here for s. This guy will cancel out. And so I'm gonna leave this guy here so that we can keep working off of it, but we're gonna plug these in. So we're gonna start over here on the left, and if we plug 0 in, that multiplies by the 3 and gets 0. So we just have 6 on this side, and then we're going to have that equal to our a times 0 plus 0 plus 10. So that means we have a times 10 plus b times 0 plus c, all times 0, so that math isn't important, is equal to 0. And from here it's pretty easy to see that a is equal to 3/5, because we can divide this 10 over to the other side, and then 6 over 10 simplifies down to 3 over 5. So I'm going to grab this guy, put our answer up here, and let me make that a little bit smaller maybe. That looks pretty bad, but we're going to be okay with it. And then I'm going to clean the board out here. It's probably an easier way to do this than the eraser tool, but I'm almost done. So, okay, so we have our a is equal to 3/5. So that's our first answer, and now we have a little bit more information, so we have a little bit more leeway on what we can do in the future. But I'm just going to keep going with the options that we have. So since this is a complex conjugate pairing, I don't necessarily want to use those zeros just so we don't get into complex math, although it is possible. So if you do feel up to the task, you can plug those zeros in and it will still cancel out just like you were expecting, but it is a little bit more difficult. So it's up to you if you want to go that route, but I'm going to try to go to our second route, which is to just pick a number. So we've already picked 0 here, so that's not necessarily an option anymore because we're not going to get any more information from that. So our next option is possibly 1 or -1. In this case, I'm just going to go with 1. So I'm going to say that 3 plus 6 is equal to our a times 1 plus 2 times 1. So that's 3 plus 10. So that's going to be 13. And correct me if I'm doing any of the math wrong in the chat, just to keep me on my toes. So I believe, yeah, that's 1 plus 2 plus 10, that's 13. And then we have our b times 1 is going to be, and then this s is also a 1, so we're going to have b plus c. So we now have a second equation. Now we can't get enough information from this only having one solution, but we can plug in another number and that should be able to give us the answer we're looking for. So if we plug in -1 up here, then we can get a negative 3, so we're going to have 3. So let me just erase this guy to make this easier. We're going to say that this is 9, and so we have 3 is equal to our -1 squared is just 1, minus 2, so that's going to be -1, and then we have a 10, so we have 9 times a, sorry, that's divided by 9a, plus our, so this b is going to be negative, and then we're going to multiply it by negative again, so it's just going to be positive b minus c. So now we have two equations to work with, and if you know, we already have a solved out, so we have two unknowns to find out, and we should have what we need in order to solve this equation. So we're going to go through this and see if we can solve this out. So I'm actually going to clean things up here. Let me grab this guy, put him down here, and then I'm just going to grab all of them. That looks pretty bad. Let me try and grab all of it, and then I'll clean up the rest of the crap later. So I'm going to cut that. We're going to get a new screen, and we're going to paste the screen down here, and do that, and we will do that. Okay, so this is the two equations we're working with. We have a is equal to 3 over 5 as our information, and then we're just going to continue on from here. So we can plug in 3/5, and we should be getting some more information. Let me just check to make sure that I am on track with my solving here, and I believe we are. Okay, so alright, so I'm going to plug 3/5 in here, so we should have 39 over 5, and so we're going to have 9 is equal to 39 over 5 plus b plus c, and then 3 is equal to our 9 times 3, so that's going to be 27 over 5 plus our b and minus our c. So what we can do is, since c is negative here and positive here, we can add these two equations together and we should cancel them out. I'm just going to leave them like this for a second since these two are already fractions. That'll make my math a little bit easier. So I'm going to add these two together, and what we should have is we should have a 12 over here is equal to, what is that? That's 16 plus 50, so that should be 66, I believe. I'm worried that I've done an error here early on, but we'll see. and that's plus b. So 12 times 5 is 60. So uh, that's 60 over 5. And when we subtract this out, we get negative 6 over 5 is equal to b. Let me just, I don't know why I closed this out. Make sure that that is correct. And I'm getting a notification. All right. So I had this open to the right page and then I closed it out. And I don't believe that is correct. So we made an error somewhere. But this is the method that is necessary for solving this out. So hopefully we can figure this out at a different time. So, but you can see that this is how we solve this out. We can plug these numbers in and get the correct answers in order to solve this out. Now, I shouldn't have gotten rid of my other screen, but we can quickly get that again. So we're going to restart this and go the other method in hopes of getting the correct answer. But it's the same for solving out for C. So once you have B, you can plug them back into the equation and get C. So if we had our 3s plus 6, sorry about that, plus 6 over our s cubed plus 2s squared plus 10s, so that's equal to 3s plus 6 over our s times s squared plus 2s plus 10, and then we can multiply that out. So our 3s plus 6 is equal to a times our s squared plus 2s plus 10 plus our s times bs plus c. So let's go the final route of solving this, and hopefully we will get to the correct answer this time. So the final route of doing this is, like I said, to equate all of the powers. So what we're going to do is we're going to look at each individual powers of this and see which ones add up to what. So let's start with the highest power. We have s squared here, and we're going to have an s squared here when the b multiplies. So we will say that a, since a is what is multiplied by s squared, plus our b is equal to how many s squares we have on this side of the equation. And since we don't have any over here, we're just going to put a 0 here. So our second equation is going to be in terms of the first power of s. And so we have what we're going to be multiplying here. So we're going to have 2a plus, and here we won't have the b because b has an s with it multiplied by an s. So we'll have a c here because c is multiplied by s. So 2a plus c is equal to, on this side we have a 3 here in the coefficient, so that's what we're going to put on this side. And then our final, the 0th power of s, is just the constants. So we're going to have 10a, and then we don't have any over here. So 10a is equal to 6. So we can check this out. This should give us what we were looking at in the first section. So if we have a, we can divide this over. That's 6 over 10, which is also equal to 3/5. So that checks out. We did that 2 different ways, and that is still correct. So it should be a little bit easier to get what our other answers are, and you'll see why I was hesitant to continue with the other example, because it's pretty obvious to see that from this equation, when we plug 3/5 over here, b is actually equal to negative 3/5. So it is not 6/5 as I said in the previous example. And so now we have 2 answers, and we just have to plug in for c. So 2a, so our 2a times 3/5 is plus c is equal to 3. So we have 6/5 plus c is equal to 3. And then what we have is, so that's going to be 6/5, and then c is equal to, so 3 times 5 is 15. minus 6 is going to be 9. So that's going to be 9/5 is what C is equal to, and that does check out with the math I have in the book. So we could even plug this back in to see if this equates out, but I think you should take my word for it. This is the actual answers. So we have our A is equal to 3/5, our B is equal to -3/5, and our C is equal to 9/5. So we could possibly just write this back out. So let me grab this guy just to make my life easier when I do this, and cut that, and then we'll write out our last answer. So I'm going to paste this, and let me clean this up a little bit. So we have the answer of 3s plus 6 over s cubed plus 2s squared plus 10 is equal to 3/5 over s plus our b, which is -3/5. So -3/5 times s plus 9/5 all over s squared plus 2s plus 10. So this would be our answer, and then you can easily go through and do the integration of this, and all of them should end up with natural logs, or with this you might have to expand this at that point, but it does make our life a lot easier when going on to do larger or more complex math problems that begin in this form. So that is the entire story with partial fraction expansion. If you have any questions while I'm wrapping up here, I'm welcome to answering them. But the one thing that I will say is that when I was taking I believe I learned this mainly in Diffie-Q, but I had learned a little bit of it. Actually, no, I believe it was Calc 3 that I learned this in college. But I've didn't think I would be using this too much, and then I got to my Intro to Vibrations class and Intro to Vibration and Controls, and now we're doing Laplace transform almost every class, and this is pretty necessary because it allows us to expand this out into chewable chunks. So what we have is now, instead of one very complex problem, we have two rather simple problems in order to answer that. So you will hear that my dog is going crazy in the background, but hopefully that will calm down in a bit. So I'm not seeing any questions in the chat, so I'm going to be finishing off this section, but I want to thank you guys for watching if you've been watching this far. After this, I'm just going to be doing my random drawing section, so you can stick around for that, and I'm just going to be getting set up. So thank you for watching so far, and I will be taking a quick break. Alright, we're back. So, this is something you might not have seen in a while. We've been having a lot of guest streams, and I've also been doing a lot of the game Tax, which I will be doing another episode of tomorrow. But we're going to get into the rhythm of having a regular stream on Saturday, or possibly a guest stream, and then on Sunday we will be doing the Tax episode. So tomorrow James is coming on the stream, and we're going to hopefully be getting a little bit into the story in terms of his perspective. I know we did a little bit on Megan's the previous weekend, but we're going to get right into the random drawing here. So you can see my random drawing sheet is right here. We have a lot of words available, and I will say that we have done, let's see, 1, 2, 3, 4, 5 of these since the beginning of this sheet. So I'm going to simplify things here and pick a random number between 1 and 20. So I will put that up for you guys to see, and you can see that the first number is 14. So that is nuts as our noun. You can see that N-U-T-S And so I'm going to click enter again. And our second number is, oh, sorry, I forgot that I have to shift things down. So that is actually going to be lube 16 for our noun, because our 14 should have been shifted down one, but then 15 was already used because it was car, so then it becomes 16. And so our noun, our verb is going to be number 15, but I have to shift that down one, so we're going to have tumble as our verb, and our final number is 1. You can see that there. So our adjective is puffy. All right, I don't know. I don't know if I wanted to draw puffy nuts, so I think I'm gonna be satisfied that we had to switch it to lube. I don't know that I'll ever say that sentence again, but you never know. So our words are lube, tumble, and puffy. So I don't know. I think that we might have an interesting picture going on here. So perhaps we have somebody that is at some sort of carnival. I'm just picturing sort of like a weird kind of slip and slide deal. So we'll have like a tarp laid out here, and we're gonna just color this in normal tarp color, and then we'll have our little person. Sorry, I'm gonna go back to the black pencil. We're gonna have our little stick person, and they're going to be. This can be the person that is watching over the ride, so perhaps they have a baseball cap, because they're just kind of looking at what's going on, and maybe taking tickets or something at the carnival. So maybe they have like a little ticket in their hand. But then what's going to be happening on the tarp is going to be a different story. So we're going to have, I don't know, what's this guy's cap color going to be? Green. That sounds like a good cap color. So on the tarp, we will have a small child. Usually I wouldn't be explaining anything about small children in terms of why lube is involved. But that's just the situation we're working in. So I'm thinking that this is going to be one of those little inflatable ball suits. That would be somewhat puffy. So we're going to have kind of like a lumpy kind of sphere around here. So to make sure that it's a sphere, I'm going to do that. That's normal sphere technology. And so this is going to be a very, we're gonna try and make this look a little bit nicer. So let's say that this part right here is going to be this slightly different color, and I'm gonna make this that color so that he's matching this guy. And then over here we're gonna have a slightly gray color, just to try to like show off the distortion, that this is like a plastic. So you can see that there is this plastic. Let's just put him like that, so that you can see the differentiation between him and the outside. So he's in this like plastic ball, and we have these lines coming off the end to show that he's going fast, because that's what fast means. If you're going fast, you have lines shooting out the back of you. So he got a running start from about here, and then he went over here and then jumped, so maybe like that, and he begins sliding. So what we see on this tarp is that they've really well lubricated the tarp in order to get across the idea that this is quite slippery. So perhaps this lubrication will be seen a little bit in the ball here. So we'll continue that line, and then we're gonna get let's grab this color again, and then color that. No, it should be maybe a little bit darker. There we go. So we can see that this kid is in a slightly puffy ball, is on this this wavy lubricant surface tarp. And then maybe we should, just because although this is a carnival, safety regulations are important, so maybe we should put a little wall up over here, so that the small child does not go sliding off of the end here. So I don't know what's this color. This is going to be a green wall. So apparently this carnival is in Seattle, but you know, I'm sure it's probably a loud carnival, but I'm sure it's quite fun, and I'm sure they're good at what they do. So um, let me try to clean this up, but I think we have a pretty complete picture here, and I'm hoping that the explanation earlier was a thorough one, and you got what you needed from it. But I think that this explanation at least has been quite thorough. Perhaps I can just color the ground colored. That is not a ground color. I'm changing color to. So maybe let's just go like that and say that it's kind of like a sandy beach or a dirt floor. I don't know. But that's what we're going for, and I think we have a finished picture. So I want to thank you guys for watching. As I mentioned, tomorrow I will be streaming with James on tax, so he's going to be continuing his story, and then we will have more streams as the week goes on, whether it be the cover on Tuesday or on Thursday with the stock market update, and hopefully by then we will have the first installment of our add-on picture with Mr. Positive, and I will be able to add my addition to that picture. So as I said, I want to thank you guys for watching, and I look forward to seeing you on future streams. So I will be signing off. Goodbye.